set of slides, please. It is on one-way functions and the worst-case hardness of time-bounded Kolmogorov complexity and computational depth by Daniel Liu and Rafael Haas and Rafael Haas.
So hi everyone. So unfortunately Yanyi couldn't come. He was supposed to give this talk, but he had an issue with his visa. So I'm going to present this work. It's about one-way functions and the worst-case hardness of Kolmogorov complexity. So I don't have to introduce one-way functions. As you know, these are the most fundamental concepts that we deal with as cryptographers. It's equivalent to all these other primitives like encryption, digital signatures, and so on and so forth. And the question that we're going to address here is, do one-way functions exist? Right? So that's arguably the most important thing that we as cryptographers should care about. And what is the minimal assumptions required to get one-way functions? Now, this question goes back a long time, in particular to the work of Diff and Hellman that introduced one-way functions. And they also suggested an approach towards this. Can we base one-way functions on the other most important problem in computer science or complexity theory, in particular, whether NP is equal to P or whether MP is inside BPP, right? So it's very easy to see that one-way functions imply that NP is not inside BPP. And the question is, can we show that NP not inside BPP implies one-way functions? And that has been often called the holy grail of cryptography. That's the question we'll try to give some more insights on. Now, this obviously is not a new problem. It's been studied for the last 50 years or so. And originally, there was some great optimism, in particular with the introduction of lattice problems. It was shown that the worst-case hardness of these very nice problems implied existence of one-way functions and more, even public encryption and so on and so forth. But soon thereafter, it was also shown that these problems are inside AM co-AM, so they're very structured, and therefore are unlikely to be MP complete. So it's unlikely that we can use these problems to base one-way functions on just NP not equal to, not inside BPP. In fact, later on, it was showed also that if we use natural classes of black box reductions, then in fact, if we want to base one-way functions on the worst-case hardness of some language L, then most likely this language L actually needs to be inside AM co-AM. Now, these are barriers. They're not complete black box barriers. There's a lot of... I can continue talking a little bit about these barriers. So these barriers that are known, they are somewhat limited in various different ways, but they seem to indicate at least that if we want to cryptography on the worst-case hardness of some language L, known techniques, those languages need to be in AM co-AM. And there's been various different extensions that have led us to this belief, at least when I started my PhD, that maybe this is inherent. Maybe all one-way functions are based on in a provably secure way on the worst-case hardness of the language needs to be structured, needs to be inside AM co-AM, and maybe it's therefore impossible to base cryptography on the other side. Now I don't have any slides. So the question is, what we're going to address is whether we can kind of get around this barrier, and can we get cryptography from the worst-case hardness of problem that's outside of AM co-AM? Okay. And in essence, we'll try to present some positive results based on the hardness of our Kolmogorov complexity style problem. So that's going to be the key results. I think I will need some slides to explain it. And some more. So we're back. So the question that we're asking is it possible to get one-way functions from something that's not inside AM co-AM? And if so, that maybe will give us an approach to actually getting towards the Holy Grail. And indeed, our key result is going to be, in fact, one-way functions from the worst-case hardness of some language or some problem, a promised problem pi, this problem is problem pi, actually, under standard assumption, is not inside AM. Okay? And the problem, as we'll see, is going to be a natural variant of the time-bundled Kolmogorov complexity problem. Now, another intriguing thing that I'll tell you a little bit more later, this is going to be a promise problem that's parameterized by some threshold. And in fact, the same problem, if you move the threshold, doesn't just characterize one-way functions, but in fact characterizes quasi-polynomial secure one-way functions or sub-exponential secure one-way functions. So it really, this object totally captures one-way functions, even the quantitative hardness of it. Okay, so towards explaining this in more detail, we're going to rely on Kolmogorov complexity, and the starting point is going to be this earlier result that Yanni and I had from a few years ago that showed that average case hardness of the Kolmogorov complexity problem characterizes one-way functions. Okay, and so average case hardness here was defined with respect to the uniform distribution. Okay, and today we're going to try to take this result and transform it into a worst case setting. Okay, so just assume worst case hardness of some related problem. Okay, so what is this problem? So Nicholas already introduced the time-bound or the Kolmogorov complexity problem. We're going to discuss a slightly different problem called just the time-bounded as opposed to Levin Kolmogorov complexity, which is defined as follows. So given a string x, I'm asking for what is the length of the shortest program that computes a string x within some time band t. And t is a function, and think of t as some polynomial, let's say n squared. So it's a function of the length of the string x. Okay? And this notion actually goes back even further than the one discussed by, this was actually already in Levin's original paper, in Kolmogorov's original paper in the 60s, this notion was discussed. And the question here is the problem of computing time-bounded Kolmogorov complexity hard or not? And this problem goes back a long time, studied since the 60s, and is closely related to something called the MCSP problem. What's cool about this problem is that there is no better uniform algorithm than just brute force search. Okay, this is known as the parabolic conjecture. Recently, there are some non-uniform algorithms that are slightly better, like very, very slightly, but at least one can break the parabol. But for uniform algorithm, there's nothing better than brute force search. So it's a very nice problem. And we're going to look at a particular promise version of this problem. In fact, that is the way the original versions were defined. You're given a string x, and you're just supposed to decide whether the time-bounded Kolmogorov complexity of the string is super high or small, smaller than the threshold s. Okay? So that's called the minimal KT problem, MKTP. So you see here the t is up in exponent. That's why it's different than the problem that Nicola introduced. This problem is nice in the sense that it's an NP. MKTP with a t below is not in NP. Okay, so it's an NP problem, and just given a string x, is it smaller than s, or is it super big? Is it called Kolmogorov random? It's a very nice open problem whether this is NP complete. Okay, and there's been a lot of great progress over the last years. Apparently, Levin tried to prove that it was NP complete in his thesis in the 60s. It failed, but there's been a lot of great progress. In fact, progress is happening in the last few years amazingly fast. We're still not there yet, but getting closer. There's also some impossibility results, but it's basically wide open, and there is great hope that maybe one can show that this is NP complete. Okay. Now, we're not going to be able to show one-way functions from just MKTP. We're going to need some extra restrictions. In essence, we're going to focus on MKTP, where we have an additional promise. We're going to make the promise a little bit more restricted. And to do so, we're going to need this notion of computational depth. So computational depth is a notion introduced by Tunis and Fortnov 10 years or 15 years ago. Talks about the distance or the gap between Kolmogorov complexity and time-bounded Kolmogorov complexity. Okay? And in particular, we will be interested in strings that are computationally shallow, where the gap between the time-bounded Kolmogorov complexity and the actual Kolmogorov complexity is small. Let's say it's less than 10 log n. Think of just log n, or 2 log n is fine also. Okay? Now, why is this notion of computational depth interesting? So as argued by Antunes and Fortnov, computational depth should be thought of as a measure of unnaturality of strings. If the depth is high, strings are very unnatural. And why is this? Well, first of all, random strings, most strings have small computational depth. Okay? And furthermore, there is a very nice result showing that it's actually even computationally hard to find non-shallow strings. So if you efficiently output some string, it's going to be actually computationally shallow. Okay? Additionally, Antunes and Fortnov pointed out a very nice connection between worst-case hardness and average-case hardness once you restrict to strings that have small computational depth. In essence, they managed to show this kind of worst-case to average-case reduction. Now, that looks very promising, and we think at first maybe just combine this result with the LP20 and we're done. We've managed to get something from the worst-case hardness of Kolmogorov complexity. The issue here is that this reduction only works in an errorless setting. So Nicholas mentioned already this gap between two-sided error and errorless. It's a huge gap. Okay? And in particular, for Kolmogorov complexity, it turns out that worst-case hardness and errorless average-case hardness are actually equivalent, as shown in a very nice result by Suchi Rara. So this does not seem to be helpful to us getting errorless average-case hardness. In fact, the LP20 result requires two-sided error average-case hardness. Nevertheless, it shows that maybe there is some hope. And indeed, what we show is in fact that MKTP problem, once you restrict attention to strings that have high, small computational depth or computational shallow, actually does characterize one-way functions. Okay? So this is the particular problem we look at. MKTP condition on this event Q that the string has small computational depth. So in essence, the problem is exactly as before. Decide whether the Kolmogorov complexity is small or large, but you all need to do it given that X has a small computational depth. Okay? So let me emphasize here. In essence, I require hardness of this problem conditional on these natural instances. Or in other words, if this problem is hard, that means that some decider needs to fail when I give you an instance that is computationally shallow. Okay? Does it make sense? So I'm assuming worst-case hardness, given the promise that the instance is computationally shallow. Okay, so now the promise is not just that it's smaller than this, but also that it's a computationally shallow instance. And the theorem that we show is, in fact, one-way functions are equivalent to worst-case hardness of this problem. Now, there's a few remarks here. We're going to use non-black box techniques to show this. In fact, as we show in the paper, we can actually provide a fully black box separation between this problem and one-way functions, so non-black box techniques are necessary. And this is really nice because it actually shows you can overcome these type of barriers we had before. The barriers on basing one-way functions on the worst-case hardness of NP, they can be overcome, at least these black box barriers, because that's what we do here. There is a separation in this setting, and we can overcome these non-black box techniques. Now, since it's non-black box, this result in a uniform setting doesn't necessarily extend to the non-uniform setting, but in fact our proof does. It's not a triviality like it is for black box result, but in fact the result works in both the uniform and a non-uniform setting. And as I mentioned, in fact, if you change this threshold, this is supposed to be an exponent, enter epsilon, if you make this threshold smaller, then this will characterize quasi-polynomial one-way functions or sub-exponential one-way functions. So the same problem characterizes, in fact, all types of one-way functions. Finally, the problem under this, as I mentioned, under some standard complexity theoretic assumptions, is not inside CO-AM, okay? And therefore, it addresses exactly this goal that's showing that we can go beyond this AM CO-AM barrier. I would also like to mention that there is this very nice result by Hirohara and Nanashima that concurrently independently also provides a worst-case characterization of one-way functions. It's a somewhat different problem, and the results are also somewhat different, but it also relies on the related notion of computational depth. There are more details in the paper. So in the last 2 minutes, I don't have much time, so I'm going to try to give you a very, very high-level idea of what is going on in what way we can get this worst case hardness and why computational depth is useful. Now, recall that the previous result shows that we can base one-way functions on the average case hardness of this Kolmogorov complexity problem. In essence, what that means is that if you can break this one-way function, you can solve the MKTP problem on the uniform distribution. Or in other words, if you have this one-way functions breaker, then you are able to solve this problem on almost all instances. That's what it means to solve it on average. So it means that you only fail on a small number of instances. Let's say less than 2 to the n divided by n to the 4. Okay? Now, if it only fails on a small number of instances, intuitively, those instances must have small Kolmogorov complexity. Okay? Because if there are so few of them, you can just enumerate them all, and therefore you can provide a short description of them. This result is not entirely trivial, because this algorithm could be randomized and so on and so forth, but in fact, you can show it that if you consider a very particular type of attacker, namely the optimal attacker, in that case, you can argue that the Kolmogorov complexity of the strings on which it fails is small. Now, this is not exactly the same as computational depth, but when you argue that the Kolmogorov complexity of something is small, you can use that as a starting point to actually prove that the computational depth needs to be large. So whenever your algorithm fails, this key idea can be used to argue that the computational depth of the instance in which it fails must be large, and therefore this falls outside of the promise. So this is just 1 minute snapshot of it, and more details on the paper. So to sum up, we provided the first one-way function complete problem. As I mentioned, this work of Hirohara Namashima provides some other problem that also is characterized as one-way function. This gives us hope that there is maybe a rich class of problems, worst case problems, that characterize one-way function. Maybe there is a nice complexity theory of this type of problems. Let me get back to this question of basing cryptography on MP not equal to P. So the result today was that MKTP hardness, worst case hardness of this, actually is equivalent to one-way function, and therefore with this result means it's equivalent to average case hardness of the unconditional problem. Okay? So the only thing that you need to do now, and in fact the exact thing that you need to do to solve the Holy Grail, is to prove that this problem is MP complete. Okay? So now that's a very algorithmic question. If you want to prove the Holy Grail, prove that this is MP complete. As I mentioned, this problem is believed to be outside AMCOM, so as far as I know, there are no barriers to actually getting this MP completeness result, except for limited type of reductions. But, yeah. Thank you.
Even that red thing is still believed to be outside even the promise version that you said. Like
yes, no, exactly. The promise version, this is what we prove in the paper, is that under this Rudish assumption, what we prove in the paper is under Rudish assumption and some standard randomization assumption. In fact, the problem that we consider, we condition on the condition thing, is not in AMCOM, yes. It was already known that it was, without the condition, it was already known it's not in AMCOM, but what we show is even under this thing, yeah.